Hi folks, Mr. Benner here, and I'm going to go over the 2026 edition of the AP Physics 1 exam with you. And 4B, wow. Anyways, let's get on with this thing. Okay, so the first thing that we had happening here was the water coming out of the water fountain there. I found myself wishing that my students had maybe watched a video that I posted for them, but only like 2 of them watched it, so it's fine. But anyways, so let's check this out. So horizontal velocity component, this is just a projectile motion thing. I know you're like, it's a fluid, but it's, parabolic and everything. Horizontal velocity is constant. Vertical velocity has a negative slope the whole time because gravity is negative the whole time. And they did tell you specifically positive y is up here. So yeah, there you go. Negative slope. The point where it's in the middle of, because it does tell you, yeah, TF, and what does it tell you about TF? Somewhere, TF returns to the same height. Yeah, so it's asking for the whole thing. So there you go, kinematics, all in a nutshell there. Let's see, so we had to derive an expression for the speed of the water exiting the nozzle. We can only use theta 0 and h1 and some physical constants in that. So let's get on with that. So I started off just kind of doing my horizontal and vertical table for projectile motion. However, I realized as I was going through this that I really didn't need the x direction for anything on this. It's really all about the y direction for this. I wrote down my 2 y direction equations, and at first I was thinking about this, and I'm like, you know what? I don't really have any info about time directly, so I decided that using that kinematics equation would probably be a better approach. And I also decided that picking the highest point would be appropriate because we wanted to use h1. And so if we do that, then our final y velocity is going to be 0. So let's see, yeah, acceleration is negative g, h1 is the change in height, and we're solving for vyi, which is the vertical initial component of the velocity. And we had to do a little bit of trig here because they wanted this what's going on here? Okay, no, they wanted the actual, they didn't want the vertical y component, they wanted the actual speed, so the magnitude of the actual velocity at an angle. So what I did is I did some trig here, and I just related the y component vertical to the hypotenuse of this triangle, the resultant of the vector there, and that's sine theta equals vyi over vi. And did a little bit of algebra there to solve for vyi, so I was able to replace vyi with vi sine of theta because they're equal to each other. And then just a little bit of algebra, divide both sides by sine of theta 0, and that'll give you this expression, which I think satisfies all of the things that they asked for, which is just to have theta 0 and h1 and fundamental constants. So 2 is fine, g is fine. Yeah, so I think that's what they're looking for. If I was going to guess on points, you're probably going to get a point for invoking the correct kinematics equation. And I can't remember off the top of my head how many points are at play here. See, this was an MR. Yeah, it is. I think there's 5 points at play here, something like that. Maybe you'll get a point for having the right trig here. Maybe a point for final velocity is 0, and maybe a point for that expression. I don't know. There might only be 3 points. I shouldn't speculate on that because there might be a couple here. There's probably one for invoking continuity or some form of that, realizing that it's area times velocity, and then actually having the full expression there. But yeah, you had to remember that flow rate is the 1/2, or one side of the continuity equation, so you had to do the area times the velocity. So if you actually got a velocity over here, and if you didn't, you probably should have said this still, is you need to multiply the area times the velocity, and they called that area, or they called that radius r0. Remember, the radius of or the area of a circle is pi r squared. So we take that area and multiply it times the velocity that we'd solve for over here. So it's just pi r 0 times r squared of 2gh1 over sine of theta 0. So there you go. Now, question 2 was quite interesting to me because as I went through this thing, I misread it the first time, and I thought that it said disk S move with the speed of 1/2 VO, and I was quite surprised when I got to the backside, and they were asking me to find the kinetic energy of disk S, because I was just like, well, they told you what the mass and then I realized I'd made a mistake. But strangely enough, it turned out that they have the same speed, and down here is the actual correct work for figuring that out. So figured, initial momentum equals final momentum. Only disk R was moving to start with, and at the end both disks were moving. We didn't know the final velocity of disk S, but we could solve for it. So using what they gave me, that the speed was 1/2 VO to the left of the disk R, I was able to plug this in, do a little bit of algebra here, and come out realizing that VF equals 1/2 VO, which, I mean, I guess this is good for the other kids that maybe misread it like I did, and you still get the right answer even if you do that. But now they wanted kinetic energy. I think I'm actually doing part B first here for you, but that's fine. They wanted kinetic energy, so 1/2 mv squared. So the mass of the disk S was 3 mo, and then we figured out here that its speed was 1/2 VO, and so you just do 1/2 3 mo times 1/2 VO squared, and you should end up, 1/2 squared is 1/4, and then 1/4 times 1/2 is an eighth, and then multiplied by 3 is 3/8, so it's 3/8 MVO. I think you would still get full credit for just this expression, the 1/2 3 mo 1/2 VO squared. Now, figuring out the momentum thing, you had to figure out what their scaling was. So before the collision, MVO was equal to 4 bars. So after the collision, maybe I wrote it over here. No, I didn't write it over here. After the collision, we did eventually figure out that this one was, okay, they told us disk R was 1/2 VO in the other direction. It still had a mass of MO, so that would be half of 4 to the left. And you could have just done conservation of energy, or excuse me, conservation of momentum with this one, because if your total is 4 bars to the right, if this one is -2, then that one has to be +6, so you'll still have a total of +4 to the right. I suspect the points here, there's probably partial credit just for conserving momentum. So as long as you still have a total of +4 between the two, you'll probably get a point, and then you'll probably get another point for having the exact correct values there. Or maybe 2. I haven't studied on how many points this part should be worth. Now, the graph here. So let's do the easy part of the graph first. And we are going to go with center of mass is the easiest one to do same, because center of mass velocity, if there are no external forces, and they told us all the info about that, there aren't any external forces. I just put my ruler on here and continue that dashed line straight on, because center of mass slope, that's what my M's were standing for. You didn't have to write anything. You just had to label them. So that one stays the same. Disk R needed to go in the opposite direction at half, and you should have gotten this one regardless of calculations, because they told you it was going half the speed. So that means that it will go, if this one went 2 blocks in one time interval, this one should go 1 block in 1 time interval, half the speed. And then if you calculated disk S properly, you should have ended up with 1/2 the original slope, because they, 1/2 VO. Now, moving on along here, you had to tell whether the change in momentum for R was greater than the change in momentum for S. So what I did is I went through and I made myself a little table just so I could get all of this right in my mind, because we all know momentum is conserved, but the way that they're asking this was a little bit weird. So they kind of had to, it's like, okay, so total momentum before and after, unchanged. Cool, that's good. Momentum of R beforehand was MOVO, and PS wasn't moving, or momentum of S beforehand was 0 because it wasn't moving. And then afterwards, they told us this one, at least they told us the velocity of this one. We can multiply it times the mass, we get 1/2, and I just moved the 1/2 out in front so it'd be easy to compare. So change from 1 to -1/2 is -3/2. This one, once you calculate its momentum, it would have 3 times the mass of the other one. That's where the 3 came from. And then it was moving at 1/2 VO in the positive direction, so that's where the divide by 2 came from. So long story short here is that this one went from 0 to +3/2, so its changes. And then we're like, oh yeah, okay, so in order for this to be 0, then those guys have to cancel out. Now, I'm not sure exactly what they're looking for here. You might have been able to get this just by saying that the 2 changes have to cancel out in order for momentum to be conserved. The way I went about this, I talked about Newton's third law, just kind of trying to get through the heat of the moment here or whatever. And I just said that they experience equal and opposite forces because they said a fundamental physics principle. So I guess that, or maybe, I guess conservation of momentum is also a fundamental physics principle, so maybe you can get the points that way too. But I just said, hey, equal and opposite forces for the same amount of time, so they receive equal and opposite impulses and therefore receive equal and opposite momentum changes. So I think I touched everything in there. Not sure exactly what they're going to be looking for full points, but somewhere in there is what you needed to say. All right, I'm going to stop here because I've only gotten through 2 questions and I've still got 2 more questions to go, and I have a 15-minute time limit on my free recorder here, so I'll come back with a version 2 of this in just a moment.